Hi everyone, welcome to the limit comparison test. So this is another test in order to determine whether series are converging or diverging. So the objective here is to use the limit comparison test to determine if a series converges or diverges. So here's what we need to do. The test is for if we have two series, one's a sum from a to n and b to n, if the limit of as n approaches infinity of a to the n divided by b to the n is finite and non-zero, positive, then we know either the series converges or diverges. Now that all depends on what we're comparing it to. So we're going to compare a of n to something else, and we're going to look at that something else and say, well, does that series converge or diverge? So this is going to be a little confusing at first. Well, it's inconclusive. It's either going to diverge or converge. Well, let's look at an example and we'll see what this means. So we want to use this test if we can't use the direct comparison test, and you'll see a video on that too when that occurs. Okay, so we want to use this test for rational functions. So if something like the summation, the series 1 to infinity of 5n squared minus n plus 1 over n cubed plus 4n plus 3. That's an example of where we can use this rule. So here's how it works. Let's look at an example. Determine whether the series from 1 to infinity of 5 divided by 2n squared plus 3 converges or diverges. So the first thing we need to do is figure out what we're going to compare this to. This meaning a to the n, a sub n, excuse me. So we're looking for things that are called benchmark terms, things that are going to affect the a sub n term. Constants don't. They're constant. 2 to the 2n squared is our key term there, our benchmark. So think about comparing it to the sum from 1 to infinity of 5 over 2n squared. Now, I can rewrite this term, 5 over 2 to the n squared. I can pull out that 5 halves. I'm looking at the series, from 1 to infinity. I did not write that there. So from 1 to infinity of 1 over x squared. Now this is great. Look, this is what I'm comparing my limit to. By the p-series test, this series converges. P is greater than 1. Okay, so if you haven't seen the p-series test, you're going to want to see that. So this is perfect. So here's what we have. We know the p-series, this what we're comparing to, converges. So I know that if I get an answer that's finite and positive, my series will converge because what I'm comparing it to converges. So let's look. So the definition, remember, the limit as n approaches infinity of a sub n divided by b sub n. So here's the rule. Here's my a sub n divided by b sub n, what I'm comparing it to. So I use some math here. Limit as n approaches infinity of 5 divided by 2n squared plus 3. Flip it here. So then I multiply across. Okay, I can simplify my 5's out and I get the limit as n approaches infinity of 2n squared over 2 to the n plus 3, or 2n squared plus 3. So we have a limit of rational functions and the powers are the same. You just divide leading coefficients, the limit is 1. Okay, so the limit is 1. That means, well, I'll leave it here, that this is a finite positive number. So this series is going to converge because what I compared my original series to also converged. So this last little slide here is just what I just said. Because the limit is finite and positive, my a sub n is going to converge because b sub n converged, what I was comparing my original series to. Okay, I wrote that here. My series converges because, hey, guess what? That series converged, and I could throw that 5 halves out there. What I was comparing my original limit to, or excuse me, my original series to, converged. So because my limit was finite and positive, my series converges. So, example 2, determine if the series from 1 to infinity of n cubed plus 1 over n to the 4th minus n plus 5 converges. So my benchmarks here are n cubed and n to the 4th. N is not going to be a benchmark because it's getting overpowered by n to the 4th. So what I did is I'm going to compare this limit to n cubed over n to the 4th, my two benchmark terms. Well, that's easy. That simplifies to this, the series from 1 to infinity over 1 over n. a harmonic series which diverges. Okay, so what I'm comparing my series to diverges. So now let's look at figuring out if our series converges or diverges. I now apply the rule. Limit as n approaches infinity of a sub n divided by b sub n, which is here. Dividing by 1 over n is the same thing as multiplying by n over 1. I multiply straight across, and you can see what I'm left here. Okay? Again, they have the same power, so we know our limit is going to be a divided by b. Our leading coefficients. These are not the same, a and b, so be careful. 1 over 1 is 1. Okay? So, now it's a finite positive number. My compared series diverges, so that means this series diverges because what I was comparing it to diverges. So, and we had a finite positive number, so now my series is going to diverge as well. So that is the limit comparison test. If you guys have any questions or comments, let me know. We'll see you next time.